Hello! What I've got for you today is a video, short one, on the conceptual version of Coulomb's law, which is ranking the net force on a charge and adding multiple forces in order to get that net force. Typically, what these type of problems involve is a series of situations. Here I've got 4 different situations, and we're going to have a bunch of charges, positive or negative, and then we'll have a dot, or sometimes it's just marked with a P for this position, and we want to know if we put a positive test particle at that position, at that dot or that P, what is the net force that that is going to feel, and rank those 4 situations based on the net force that test particle is going to feel. And we are always going to assume that the separations are equal, even if they don't look equal, because, well, okay, between the font and my drawing skills, it usually isn't equal. We're going to make that assumption. So this is, as I said, a conceptual version of Coulomb's law. Coulomb's law is the charge, the force between 2 charged particles, and it involves the constant K, and that's just a constant, it's the same number all the time, the charge on the first particle, the charge on the second particle, the distance between them, and then this, Coulomb's law, we kind of think of it as absolute value because it only gives us size. This equation only tells us the size of the force. The direction of the force we have to consider based on looking at the situation. So here, we've got this situation where all of our charges are equal and the distance between each of these things is also equal. We want to know what is the total force on a test particle, positive test particle, placed at the dot. So we're going to run through number 1. So we'll start with A. And A, we have a positive, a negative, here's our dot, and a positive. And we're imagining that we're putting a tiny little test charge, positive test charge, at that spot, at our little dot. We want to know what this would feel from the other charges around. And one of the things you need to watch very carefully is that we want what this thing feels, not what it exerts on others, not what it's doing to the other charges. This is you. You are standing here, and you are positive, right? You're positive. So what do you feel? This is you. What do you feel? I don't care what the other ones feel, what they're feeling. That's not the question. What does this charge right here feel? All right, let's do it. We have a positive test charge here. There's a positive charge on the right. Positive and positive, same sign. They're going to repel each other. So from this positive right here, I'm going to have a force going to the left, because it's a repel, it's pushing me away, and it's 1 unit distance away. So for 1 unit distance, I'm going to call that a 1 unit of force. We don't care what the actual number is because we're just ranking. We're not actually calculating what that total force is, because we need to know what the size of the charges are, for one thing, and the distance between. We're just ranking, so we just want to be able to compare against other situations. So for 1 distance away, I'm going to call this a size 1 force. So right now, I'm feeling a push of 1 to the left. That's from this one. Okay, we've taken care of that one. Now I'm going to take this one. From this one, it's a negative, and I'm a positive. We're going to attract each other. So it's attracting me towards it. It's also 1 unit distance away. So I'm also going to have a 1 unit force pulling to the left. So this one is pushing me away. This one's pulling me towards it. I've taken care of that one and that one. Now let's look at this one. This is a positive. I'm positive. We're going to repel. So this thing's going to be pushing me away. So I'm going to have a push to the right. How big is it? Now it's twice as far away as these. So if we have 1 unit distance giving 1 unit force, if we double the distance, what happens to that force? I'm going to double this R down here, the distance. And what's that going to do to the force? Well, it's going to make it smaller because the R is in the bottom. And that should make sense because we know that as the charged particles get farther apart, the force between them is smaller. It's harder to see the effects if they're far away. It's easy to see the effects if they're close. So smaller. And you might say it's a half, but it's not. The distance is squared. So for 2 units of distance, away, the force goes down, but it goes down by 1/2 squared. So we have 1/4 the force. So for a distance that's doubled, the force is going to go down by a factor of 4, 2 squared. Which means I have a push to the right of 1/4. What is the net force? That's what I want to know. And I'm just going to add them up, but they are vectors. Forces are vectors, size and direction. So don't forget to take into account the vectors. This is not 2 1/4. It's not 1 + 1 + 1/4. We got different sizes, or directions, excuse me. So for A, it's going to be 1 + 1 + 1, nope. I just made that mistake, didn't I? 1 + 1, let's try this again, -1/4. So for A, the total is going to be 1 + 1 - 1/4. Well, that's 1 3/4. So A is, in this kind of weird little world we've created, the size of the force on a test particle right here is going to be 1 3/4. All right, now we're going to try it for the other 3 situations. B, what do we have? We have negative, the dot, negative, positive. All right, so I'm standing right here and I'm positive. What do I feel from the other charges? Take them one at a time. Let's start with this one. This is negative, I'm positive, we're attracted to each other. So this is going to be pulling me towards it. I'm getting pulled towards that negative. It's 1 unit distance away, so it's a one size force. This negative is going to be attracting me, so this is also pulling me towards it. It's 1 unit distance away. I got a 1 going to the right. This positive, I'm positive, we're repelling, so I'm getting pushed this way, and it's 2 distances away, which means we have 1/2 squared, 1/4 of the force. There's 1/4 going to the left. For B, I'm going to have 1 + 1/4. So these add together, and then I'm subtracting that one. So 1 + 1/4 - 1, well, these two cancel each other out. That's going to give me 1/4. So B, the net force, is 1/4. All right, C, here's our dot, here's our negative, a positive, and a negative. All right, we are here, and we're positive. And I better move this because I know I'm going to run out of room there. I'll race a little bit. Okay, so for me standing here and I'm a positive, take them one at a time. This negative is attracting me, so I'm being pulled towards that negative with a size 1 force. This positive is repelling me. I'm being pushed away from it with a size, let's see, it's 2 away, so it's 1/4. And this negative is attracting me, so it's going to the right. And what's the size of that force? Make a prediction. So if it's 3 unit distances away, how big is the force that you feel from that charge, 3 distances away? Well, got your prediction? It should be 1/3 squared. So to the right, I have 1/9. For C, it's going to be 1 + 1/9. These two add together, and then I'm going to subtract 1/4 off. 36 is a common denominator. 36 + 4 - 9/36. All right, 36 + 4 is 40 - 9. 31/36. The size of the net force on the test particle for C is 31/36. That's hard to say. Last one. If we have D, we have the dot plus, plus, plus. So we put our little positive test charge right here, and what does it feel? Well, from this positive, it's getting repelled, so it's being pushed away with a size 1 force. This one repels it, pushing with a 1/4 size force, and again, another repel, this time at 1/9. Total force here is 1 plus 1/4 plus 1/9, so that's 36 plus 9 plus 4, 36ths. That's 49/36. Okay, so D is, let's get that out of the way. So D, the net force on a positive test particle for situation D is going to be 49/36. And now we're almost done. We just need to rank them. What is the biggest one out of those 4, and which is the smallest? Now we had to take into account direction when we were adding the forces together, because the forces add together, but you'll note I was ignoring left-right. This quarter, I'm just saying it's a quarter, because we only care about size. We don't care it's a quarter to the right, it's a quarter to the left. If we had 2 1/4s, I'd set them equal. I don't care what direction they're going. So for this type of problem, I just want the number. I don't care about which direction the total force is. All right, which one's biggest? Well, clearly that one. So A is the biggest net force, and that's bigger than, well, that's 9/36. So D is the next one, and then that's bigger than C, which is bigger than B. So the answer to this question, A, then D, then C, then B. A has the biggest net force on that little test particle. B has the smallest net force on that test particle. And that's just the basics of this kind of problem. This is a conceptual Coulomb's law problem where you have to know what Coulomb's law is, and you have to remember that forces are vectors and that the separation is squared, the distance between them is squared, which means we have to go as 1/4 or 1/9. There you go. Good job.